on G mod H is metrically ergodic. Whenever you map this space into U, well, you can pull back the metric from U to G mod H. Whenever you map it measurably, you will get a measurable, separable, semi-metric on G mod H, but it must be trivial. So it means that all points have images with distance 0 from each other. It means that the image is constant. Constant G point, G fixed point. And somehow, it is useful for me to have this term over there, this corollary, in that form. I will explain why, or it will be clear why in the near future. Of course, this is just a synonym. But now, before ending this hour, I want to give another example. Another example, or another class of examples. If X is doubly ergodic, so I'm in the setting discussed before. X is elementary space, and X is doubly ergodic. This means that G acts not only on X, but on X squared with the product measure is ergodic. Then, actually, X has the very strong property of being metrically ergodic. We give proof of that. Consider the map from X times X. Assuming we have some map to some U. Consider the map from X times X to U times U. Now, this should be the G invariant map, because the metric is invariant. Is G invariant? Hence constant. It means, well, if this constant would be 0, this means that every 2 points in X goes to the same point, and the map is constant. The map X to U. So let us discuss what is this constant is. I don't know, something else, 1 or epsilon or whatever, 1 million. It means that X sits as a separated set inside U, the image. But U is separable, and X is not. Well, I have to argue about this, but since, let me start by saying, since X has no countable factor, the image in U is either a fixed point or some uncountable discrete set. I should explain this. Don't look at me like that.
I'm not arguing that, but okay, it's constant.
Unhappy in general.
It's constant up to set of measure 0, which lies somehow in this product, and then
Yes, it's essentially constant. It's the same.
It's essentially separated set. No, I just cringed.
Okay. No, okay. You have the right to get a little shiver here and beware about the details. I'm not giving.
I'm trying to digest.
Okay. So let me finish though. We deserve the break. Since there's no countable factor, so the image of X in U, I claim, and I will explain this in 1 minute, is not countable by separability of U. x times x, ta ta ta. I mean, fx is 0, and the image of x is essentially constant in U. And now I need to explain why if G acts on X squared ergodically, then it does not have a countable factor. And let me do it orally and rush to a break. This is really very easy. Well, if we had a factor y of x, the action of G on y, a factor means just such guy that you have an equivalent map from x to y. This is what I mean by a factor. Then the action of G on x squared would be, if this is ergodic, then this is ergodic as well, right? If I would have an invariant function here, I could put it back here and get an invariant function here. No problem. But if this was countable, the measure would be atomic, right? It will charge positively at atoms, and then I will have in y squared at least 2 invariant sets. Unless y is a point, I will have the diagonal and the rest. These are nice things to keep in mind, that measurability of the diagonal in x squared, sorry, positivity of the measure of the diagonal in x squared is equivalent to having atoms in x. This is a little thing that is very useful to have in mind. And since we can't have it, we can't have 2 orbits here, it can't be countable.